Well, hello everyone, this is Chris again. I am hoping to get this video out to you guys before I head out. Today is Tuesday, it's about 8 o'clock in the evening, about the quarter till. So hopefully I can get this out sometime this evening. The issue is that I am leaving tomorrow, partially for business, partially for pleasure, so I do apologize that I'm going to go out and have a little fun. But what's occurring is for the rest of the week I'm going to be going up to Ruidoso to something called Winterfest. Yes, we actually do get some snow down here in New Mexico in the higher elevations. We have actually a significant number of mountains in this state, which actually surprises a lot of people, believe it or not. People don't realize just how diverse the environment is in this state. It's a really beautiful place. Can't say enough good things about the outdoors in this state. But anyway, I still wanted to get another video out for you guys before I head out. I'm not sure if I'll be able to get one in this weekend. We'll get right back into the full swing of things at school. I've got another semester left, hitting it hard and heavy, so I already have a fair amount of homework and studying to do, but I still plan to get this one out for anybody who really cares all that much. But anyway, what I'd like to talk about is I'd like to continue on with the lines of flow. And what I would like to do is I would like to now talk about some of the equations. We talked about the Reynolds formula and how it gives us a dimensionless number that says, hey, I have this kind of flow or I have that kind of flow. Mainly 2000 being kind of our limit between laminar and turbulent flow. But I just want to kind of look at another aspect of how a fluid flows. So if you remember from a little earlier, I'd drawn a picture of a pipe. And I said, okay, so here I have my pipe, and I have a fluid. And that fluid is going to flow through a pipe. Could be air, could be water. We could imagine that it's gas flowing through this pipe. Now, to get something to flow through a pipe or a tube or a conduit, I need something called a driving pressure, or delta P. And all a driving pressure is look, I have a pressure here, and we'll just say that it's 10 units of pressure, and then I have a pressure here, and that's 5 units of pressure, we'll say, on the outside. And the difference between these two pressures, the delta P, if you will, in this case it would be 5, a difference of 5 units, is known as the driving pressure. Do not confuse this with the delta P on the compliance and resistance formula that we talked about earlier. This is a different concept than those. It's not entirely different, but we're talking about a different aspect of fluid dynamics. So driving pressure in this case. And I said, look, you need to have a gradient, right? We need some sort of gradient to drive this fluid. Now we know, or you can probably intuitively guess that, you know, we have gas. And if I take a container of gas here, gas molecules, we know that gas has this property of compressibility. I can compress the gas down, and when we talk about the gas laws, which I'll probably just do a video on some of the gas laws, as I compress that gas, the volume decreases, and what law has an inverse relationship between volume and pressure? And of course that would be Boyle's law. So as the volume decreases, as I push it and squish it and squeeze those molecules in, the pressure is going to increase. Now, fluids, or not fluids, but certain liquids, on the other hand, are a little different. They are generally what we call incompressible. Now, there is a certain amount of compression with liquids. but generally for our cases, we can say they're non-compressible. And if I compress water, generally, obviously, there's a little bit of compression that can occur with water, but generally, water is incompressible. I can't make it smaller. It fits a certain volume, and that's it. And that's kind of the, you remember from physics, or if you've taken some physics, and they talk about a hydraulic ramp. And I have something like this. I have a little device like this, and then I have maybe a car or a truck on this ramp here. And I put a force down on this little small disc or piston or whatever, and it has a certain area. There's a certain force. The pressure is going to increase here, but because this liquid does not compress, that force is going to be transmitted over here, and it's going to push this side up. And we know that we can, using a little bit of force, I can lift a large vehicle. Now obviously, because of conservation laws, which is something I'm going to talk about in another video, this isn't something, looks like it's something that may violate those laws, but really what happens is I'm putting the same amount of work in, right? I have to push this thing down really, really, really far to get this to move up a little bit. So it's not like I'm getting nothing for free. But the main point is that this fluid, this hydraulic fluid, if you will, is incompressible, and I push in and that goes up, I push down and that goes up. With a gas, I could push that in and it would compress, and this other side wouldn't necessarily have to go up. Or, yeah, with a gas, sorry about that. Okay, now the law that I'm going to talk about is more relevant to this here. It's more relevant to a liquid, and is more relevant toward a non-compressible liquid with laminar flow. Okay? So it doesn't have quite the application for compressible fluid with turbulent flow. But some of the basic underlying principles I'm going to talk about will definitely apply, but they will not apply exactly as the formula states when we take in gas into consideration. So I just want to tell you guys that caveat. And this formula is actually derived from a set of formulae known as the Navier-Stokes equations. And the Navier-Stokes equations are a very, very complicated set of equations they're basically derived from Newton's second law of the conservation of momentum, or what you guys are probably familiar with, the force equals mass times acceleration, F equals ma. And we're able to derive a force law for fluids in a very general, very broad kind of way, nothing really accurate. It's actually one of the great mysteries of math right now. But from those equations, we can derive this equation. So it's really more for special situations, but it still has some pretty profound implications for what we do in respiratory therapy. And the name of this is Poiseuilles' law. And let me just go ahead and throw this up here. It's P-O-I-S-E-U-I-L-L-E-S. Poiseuilles' law, Poiseuilles' principle. I believe it's Poiseuilles, it's French. If you live down here and you say it's Poiseuilles' law, I would be alright with that. I would not make fun of you. Now, if you're from up north, say in Wyoming, and you say Poiseuilles' law, we're going to have to make fun of you all day long. So certainly a little bit of context there. But Poiseuilles, I believe, is the appropriate enunciation. Year of high school French, and I probably butchered that. Well, anyway, continuing on. So Poiseuilles' law is written or derived like this. There are other derivations of it, but this is the one that is fairly relevant, or more relevant to us. Okay, so delta P equals AULV. Sometimes this will be written as a Q. I'm going to write it as a V with a dot over it because we're more familiar with that in respiratory therapy. And that is pi r to the 4th power. Okay, let me break this down. Delta P, well, we know what that is, right? That's the driving pressure here. So the driving pressure equals 8 times mu. What is mu? Mu is the the viscosity. Sometimes you'll see that written as an N, but we'll just keep it as a mu for now to avoid the confusion. L is the length of our conduit here, has a length L. V with a dot above it or a Q, well, we know what that is, that's flow, right? Sometimes Q is cardiac output in liters per minute. It means the same dang thing, it's flow. And then we have pi r to the 4th power. We know what pi is from the pi video. And then r to the 4th is just the radius. That is the radius here, r, of our conduit. Okay, so that's what it is. How do we apply it? Well, let's talk about it. So delta P. Now remember, anything in the numerator is directly related to what we're looking at. It is a direct function of this. So anything increases in here, the delta P is going to increase. And hopefully that makes sense. If my viscosity increases, I'm going to need more pressure to move that viscous liquid, or that viscous fluid. If the length of my conduit increases, obviously I'm going to need an increased delta P to maintain a certain flow. And obviously if the flow increases and everything else stays the same, I'm going to need more driving pressure to drive that flow, right? I'm going to need a bigger gradient to have more flow going through that conduit. So all of these are directly related. And then we have our numerator here, and we remember our numerator is now inversely related. So what this says is, really what it says is, as the radius of my pipe, so if this has an R, a radius of R1, and we decrease that to R2, so maybe this is 1 unit and this is 1/2 unit, what does that tell us? Well, that tells us that the delta P is going to what? If the radius decreases, delta P is going to increase because there's an inverse relationship. And not only is it's not going to increase just a little bit, it's going to increase a whole hell of a lot because I've got my radius to the 4th power. So r to the 4th power. This decreases by half. I have a significant increase in my delta P to maintain the same flow. Likewise, if my radius increases, delta P is going to decrease, and it's going to decrease very significantly. Now, even though this is for a liquid, and we're talking about laminar flow, we can make some general assumptions here. And I think the most profound assumption for respiratory is, look, if I have an airway and that airway swells, or I have bronchospasm, and I decrease the radius of that airway, the driving pressure required to maintain flow through that airway is going to increase quite a bit, significantly. Where does that driving pressure come from? That comes from us. It comes from our diaphragm, our intercostal muscles, and so on. So that means that our work of breathing increases significantly in those situations. Likewise, it will decrease if we can reverse whatever is causing that, the radius to decrease, or give a bronchodilator perhaps. Another application is going to be fluid resuscitation. And you know, the classic scenario is a doctor wants to put in a central line and it's a really long skinny catheter because he wants to get lots of fluids into our trauma patient, gives them lots of blood. But what could we do instead? Well, we could put a short, large catheter, a big peripheral IV that's short and wide, and I can get a lot more fluid in there according to Poiseuilles' law. So hopefully you guys found that intuitive, and I hope to get this out today. Thanks for sticking in with me, guys. Bye-bye.